The other important thing to recognize is that with the alkene additions of an electrophile like bromine, Br2, no catalyst was required. That's what we mean by, these aromatic compounds react less readily than traditional alkenes. So with the aromatic compounds, you need a catalyst. And the catalyst is usually an iron that's connected to three other, well, remember, this is an ionic compound. Anything with a metal in the formula is an ionic compound. So this is like an iron +3 ion with 3 bromide ions, FeBr3, okay? Now you'll see in a little while that it could be, we're trying to add a chlorine to the aromatic ring. In that case, you just change the catalyst to an iron chloride rather than an iron bromide. The key is that iron behaves as a Lewis acid, and you'll see that in the mechanism, okay? So bottom line for this bullet here is that a catalyst is required. It's an iron 3 bromide. Okay, so here's just the overall general reaction that occurs. So you have your benzene ring, and you have some bromine, Br2. In the presence of a catalyst like iron 3 bromide, you end up substituting one hydrogen with a bromine, and then the other product would be HBr, hydrobromic acid. So hydrogen pops off, one of the bromine atoms, there's 2 bromine atoms here. One of them goes on the ring, and the other takes the hydrogen with it to form a mole of hydrobromic acid. Okay, so here's the mechanism that I was talking about. So remember that I said that the term that I used for this catalyst was that it serves as a Lewis acid, right? So this is a Lewis acid. And so also this is color-coded to point out that this, due to polarizability, can be thought of as like the partial negative and partial positive end, and this is the partial negative end of the Br2, okay? So because this has those lone pairs on it, as nucleophiles do, it will act like a Lewis base and form a bond with that iron in the Lewis acid. And that's why if you go down, it goes from FeBr3 to FeBr4, right? Because that bromine that had the partial negative charge on it behaved as a Lewis base and formed a bond, another bond with the iron. Well, that gives the overall polyatomic ion a negative charge. Okay, now this iron was neutral, but since it took on that Br minus, now it's got an overall negative charge. And so that other bromine just goes full bore positive, which is an electrophile, right? Anything with positive charge, partial or full formal positive charge is going to behave as an electrophile. So that's where we get the electrophilic part of the electrophilic substitution. Okay, now, then is where it sort of behaves like an alkene reacting with an electrophile. That pi bond acts as the nucleophile, so that acts as the nucleophile and attacks that electrophile, the Br+, forming the bond. But that position still has a hydrogen on it. And so here's where the difference is between this type of reaction and an alkene electrophilic addition. So remember, when this reaction occurs, when this pi bond reacts with the electrophile, it gives up its aromaticity. It's no longer aromatic. It doesn't have that, it doesn't obey the Huckel rule. It doesn't have that conjugation pattern that you need. But it's like, oh, wait a minute, I'm not, I don't really want to lose my aromaticity. I want it back. So the way that it does that is it takes that pair of electrons that's connected to the hydrogen and it moves it back into the ring. So those electrons just move back into the ring, and that ion, that that polyatomic ion with the iron in it, that just takes away the hydrogen, and you get a molecule of HBr, and you get the catalyst back. But the other thing you get back is you get the aromatic ring back, and so that's the compelling factor. Okay, it doesn't stay in this intermediate state because it wants that stability that comes along with being an aromatic ring. Okay, so that's the mechanism of the electrophilic substitution of an aromatic ring. Okay, so as I said, it kind of wants that extra stability back at step 2 there from taking those electrons and making it an aromatic ring once again. Okay, so for example, let's say that we have this molecule, which hopefully you remember the name of that. That's toluene, right? So we want to put a bromine on there. Monobromination of toluene gives a mixture of 3 bromo-toluene products. We're going to draw and name them. And this overlaps with something that we talked about last week when we characterized the spatial arrangement of the substituents. Remember ortho, para, and meta? That's going to show up here. Okay, so one thing we can do, and again, drawing benzene rings is not necessarily my strong suit, but one of these bromines is going to end up on the rings, and it can end up in 3 different positions. So let's say that we have one where okay, so we've got our toluene right there, CH3, And so 1 is where we put the bromine right next to it. Okay, so that would be our ortho. Okay, but another product would be, and again, I got to draw these benzene rings, it takes a second, where the bromine ends up 1 carbon separate from it. So that would be in the meta position. So that's the bromine in the meta position. And then finally, we have the third potential product. Start with toluene, and we substitute the bromine on just directly across from it. So remember, that is called para. Okay, so ortho bromotoluene or meta-bromotoluene or para-bromotoluene. That just looks a little prettier. Ortho bromotoluene, meta-bromotoluene, and para-bromotoluene. Okay. All right, so as I said before, that we can do this with other halogens like chlorine, Cl2, but just you change the catalyst. And here's one example of that. If anybody took Claritin this morning, this is a reaction that is used in the production of that allergy med. So aromatic rings will produce chlorobenzenes when they react with chlorine, Cl2, with iron 3 chloride as a catalyst, FeCl3 as a catalyst. So pharmaceutical agents such as Claritin are manufactured by a similar reaction. And I think you've got this reaction diagram in your handout already. All right. So it's just a substitution reaction, electrophilic substitution reaction. We substitute one of the hydrogens on a benzene for something else, an electrophile, in this case, and in the previous case, just a halogen, chlorine, bromine. But it happens with many, many different things, which is what we go into in the rest of the lesson for today. Okay. So, actually, one more halogen we got to talk about. So if you want to do a substitution with fluorine, it takes a special reactant. This one right here, the FTEDA BF4. Okay, and you've got this reaction diagram also in your handout. So what I expect really for you guys to know is just the name. Okay, so you don't have to draw the structure, but if you can just recognize that name, goes along with electrophilic substitution of a fluorine on a benzene ring. That's the main thing. Because as you can imagine, fluorine is the most electronegative element on the periodic table. So it's rather difficult to make it adapt a formal plus charge, a positive charge. So this is one of a few reactants that can actually do that. Okay. And we're going to get into this tomorrow, but you can see that there's a mixture of the ortho product and the para product. Okay, and there's a reason for that, but we won't talk about that today. I'll just save that discussion for tomorrow's lesson 2. So we talked about fluorine, we talked about chlorine, we talked about bromine. Well, what about iodine? Can you substitute iodine on a benzene ring? And the answer is yes, but you do it with just a different catalyst. In this case, you do it with copper 2 chloride, CuCl2, copper 2 chloride. So it actually oxidizes the iodine molecule, I2, into electrophilic iodine. Okay, so that's shown in this diagram right here, which is also printed in your handout. So the I2 essentially becomes 2 I plus ions, which is kind of weird. But with this, copper 2 chloride also present in the mixture, you will get that. So it just, again, does a electrophilic substitution reaction. If you have a base present, then it takes away that hydrogen. The benzene ring gets its aromaticity back, and you get iodobenzene. We've gone through all the halogens. Now let's talk about other things that we can substitute onto the benzene ring. One of those is a group that we've introduced recently, the nitro group. Okay. And the way you do that is with a combination of concentrated nitric acid and sulfuric acid. Okay, so you can imagine something you wouldn't necessarily want to get on your skin, but it works really well for doing this, for substituting a hydrogen with a nitro group. And it does that with this intermediate ion called the nitronium ion. It's an electrophile. As you can see, it has a formal positive charge. Okay. So it reacts with benzene to produce nitrobenzene, where we substituted one of the hydrogens with a nitro group. And so the diagram you see here, which is also in your handout there, just goes through how that occurs. So it turns out that sulfuric acid, H2SO4, is a stronger acid than nitric acid. How do you know that? Well, because when you mix the two together, the sulfuric acid actually donates one of these acidic hydrogens to the nitric acid to produce a water molecule, this right here, this H2O right here. And we know that now, since we've talked about leaving groups and SN1, SN2, E1, E2, we talked a lot about the characteristics of the leaving group, that a water molecule is a really good leaving group. So this H2O is now going to leave, and then that leaves us with a product that is a nitronium ion, which is a really good electrophile because it's got a positive charge. So this really good electrophile, nitronium, will then react with the benzene ring according to the mechanism that we've already looked at. Okay, and so then the water molecule comes along and behaves as a base to take away the hydrogen so that the benzene ring can get its aromaticity back, and you end up with the mono-substituted nitrobenzene. Okay. All right, so that's how you throw a nitro group onto a benzene ring. Okay, well, what if you wanted to throw like a sulfone group? Okay, well, you can do that too. You do it with something called fuming sulfuric acid. Fuming sulfuric acid. So what is that? Well, that's just a mixture of concentrated sulfuric acid, H2SO4, and sulfur trioxide, SO3. Because once again, when you mix those two things together, the sulfuric acid actually donates a H plus to the sulfur trioxide. And you'll notice that sulfur trioxide, before it takes on that hydrogen, has got a formal negative charge and a formal positive charge. Well, that hydrogen, when it gets added to this oxygen, it neutralizes that negative charge. So now this thing is a really good electrophile. It's got that positive charge on it. So this is going to behave as a fairly strong electrophile. So it will undergo electrophilic substitution, just like all those other reactions that we've already talked about. So again, it reacts with the benzene ring, and in order for the ring to regain its aromaticity, it loses its hydrogen to some base that happens to be around. And actually, the base is HSO4 minus. And so you get the benzene sulfonic acid. Okay, so you can throw a nitro group on the benzene. You could throw a sulfonic acid group onto the benzene. Okay, and so I guess now I got a quicker question for you. I forgot about this one. So think about this. So we want to produce toluene, which is pictured over here on the right. Okay, and remember that TNT stands for trinitro toluene. There's one nitro, there's the second nitro, there's the third nitro. So trinitrotoluene. So which reagents do you think we're going to use to do that based on what you've got in your notes so far? So think about it, submit your answers. So we can throw halogens on there, we can put a nitro group on there, we can put a sulfuric acid group on there, but here's the other really, we're going to get into two situations that have a lot of utility, okay? Very useful. We can put an alkyl group on there. We can put more carbons onto the benzene ring, okay? And we do this through something called a Friedel-Crafts reaction. That's the name of this type of reaction. It is in electrophilic aromatic substitution, but it's just a specialized version. So it's got its own name, the Friedel-Crafts reaction. So it's where you're substituting an alkyl group for hydrogen on a benzene ring. All right, it involves a catalyst, but it's a little bit different. It's not iron 3 bromide or iron 3 chloride. Okay, but it involves the same intermediate, same mechanism, same intermediate. It involves the reaction of an aromatic compound with an alkyl chloride to yield a carbocation electrophile. So you start with a benzene ring, you start with an alkyl chloride, and you use this catalyst, which creates a carbocation, serves as an electrophile, and then goes through the reaction mechanism that we've already looked at. Okay, so typically the catalyst used is aluminum chloride, AlCl3. And so what you see here is just a typical, it's an example of a Friedel-Crafts reaction. So our alkyl chloride, in this case, is just a methyl chloride, okay? So anytime you just want to add a string of carbons to a benzene ring, first of all, make it a halogen, and then find yourself some aluminum chloride, which serves as a catalyst, mix everything together, and through the Friedel-Crafts reaction, you will add that organic group, that alkyl group, to the benzene ring. Okay, so as you can see, it substituted what was a hydrogen here at this position with the methyl group. Okay, and then the chloride that was on that methyl group goes along with the hydrogen that was on that benzene ring to give you the HCl. That's your byproduct. But the main product is that, oh, you know what? By the way, this has got I didn't notice this till just now, but there's a error in this. You should have make sure you fix that on your handout there. There should be a double bond right there. All right, so again, here's the mechanism, which again is just adapted to the Friedel-Crafts situation, but it's really the same mechanism that we showed you before. So, but this just kind of highlights where you get the carbocation. So again, let me just draw some more stuff on here. So this chlorine can act as a nucleophile. It's got those lone pairs of electrons on it. And this aluminum is like our Lewis acid, right? A Lewis acid accepts electron pairs. This Lewis base is going to donate the electron pair. So in the process, what happens is this bond between the carbon and the chlorine, well, it just dumps the electrons onto the chlorine. Okay, so it makes it a chloride, and that's where you get the AlCl4 minus. Okay, but then you get the carbocation, which acts as your electrophile. So then it's just the same mechanism. It reacts with a ring. The ring loses its aromaticity, but it wants it back. So it takes the electrons from that bond with the hydrogen to pump them back into the ring so it can become aromatic again. And then the catalyst comes along and takes on, essentially serves as a base. It takes off that hydrogen and you get a HCl molecule as a byproduct, and you get the alkyl substituted benzene ring as your main product. Okay, that's the Friedel-Crafts reaction. Okay, so there are some limitations to this that we want to talk about. First of all, only alkyl halides can be used. I put this list because it can be any of those halogens. But the real limitation, what I mean by that, is that you cannot use an aromatic or vanillic halide. So like a benzene, like fluorobenzene or bromobenzene, you can't use that in a Friedel-Crafts reaction, nor could you use a vanillic. And remember, a vinyl group is where you got that double bond. Well, let me just draw that to remind you what we mean by a vinyllic group. So if you had something like this, where you had a propyl group, where there's a carbon, and then there's a double bond between those two carbons, and then there's this primary carbon. So let's say that this was like a bromine, or this would not work for a Friedel-Crafts. This is what we would call a vinyllic, a halide. Okay, so I should have changed colors. Let me clear that away and do it 2 different colors. So a vinyllic halide would be something like, something like that. Where you got the vinyl group right there. So that's the vinyl substituent. Okay. But, this won't work if you're going to do a Friedel-Crafts reaction. Okay. And the other thing the other situation where it won't work is when your benzene ring, if it's already been substituted, and the substituent is what we call electron withdrawing. And we'll get into that more in depth in lesson 2 tomorrow. But for now, just get it in your notes, I guess. So it won't work on rings that already possess a substituent that is electron withdrawing. So if, and this just shows you in the diagram graphic that you've got in your notes, if this substituent that we're abbreviating with a letter Y, if it happens to be any of these groups over here, and there are lots of them, but you can see they've got something in common. It's something that's pretty electronegative, like nitrogen or a carbonyl group. All these CO2H, CO2CH3. That all involves the C double bond O, the carbonyl group, and so that's an electron withdrawing group. Because those are situations where you cannot do a Friedel-Crafts reaction. And again, that will make more sense after we've done lesson 2. Okay, now the other problem is sometimes Friedel-Crafts reactions happen that they just don't want to stop. They want to keep going. They want to happen again and again as much as possible. So termination of the reaction at a single substitution is difficult, often leading to multiple substituents. So bottom line is sometimes it's hard to stop the Friedel-Crafts reaction, just kind of a cascade effect, avalanche. So for example, let's say that I've got a benzene ring and I've got this tert-butyl chloride in the presence of an aluminum chloride catalyst. Okay. Yeah, you'll get some situations where it substitutes once. That's your minor product, though. The major product is actually it substitutes it twice. Because once, and again, this will make more sense after we talk tomorrow with lesson 2. But the thing is, once you put a tert-butyl substituent on there, it activates the ring. It makes it even more reactive. An electron withdrawing group actually deactivates the ring. That's why you can't do a Friedel-Crafts on it. But if you put something like any sort of electron donating substituent, like a tert-butyl group, something that donates electrons, then it's going to activate the ring and make it more reactive. Okay. All right, now the other thing that you got to watch out for, and this is something that we have talked about in prior weeks, you can have a shift to make a more stable carbocation which may get you a product that's different than what you're shooting for, what you really want. Okay, you can have a hydride shift or an alkyl shift that gives you a more stable carbocation, and that's great, but that might not be what you're looking to produce. That may not be the desired product. So occasional skeletal rearrangement of the alkyl carbocation can happen. So this occurs more often with the use of a primary alkyl halide, occurs more often with the use of a primary alkyl halide. And so what happens is you get that hydride shift or alkyl shift, because sometimes a hydrogen will shift to a new position, get rearranged, or an alkyl group even will shift over, get rearranged in order to generate a more stable carbocation. So this is just a couple examples of that. So let's say that I want to put this 1, 2, 3, 4, this is a straight chain butyl group on a benzene ring. You know, I want it to have a tail, like a 4-carbon tail. Well, actually what you're going to end up with is a branched chain on there. And the reason why is because you get a hydride shift. If you think about what happens, this chloride comes off, that Cl comes off, and you get a primary carbocation. That positive charge is on the end carbon. Well, if that carbon 1 over just rearranges a hydrogen, then you end up with a secondary carbocation, which we've learned is more stable. So this one is a primary carbocation. Remember, this is a primary carbocation. But if we just move that hydrogen over, then we end up with a secondary carbocation, which is more stable. Okay, that can happen with a hydrogen, but also remember that it can happen with a alkyl group. So that's what we have in our next picture here, which is also printed out in your handout there. So in this case, let's say that I want to put a it's an isopentyl is what the common name for it, but I want to put that isopentyl group on a benzene ring. Okay, well, you don't even get that. It won't even react that way because your intermediate carbocation, remember that chlorine comes off to give you this intermediate carbocation, which is primary once again. So this is another situation where you've got a primary carbocation. Sorry, primary carbocation, not 10. But then this whole methyl group moves over onto that, you know, to cancel that positive charge when it does that, but it puts the positive charge on a tertiary carbons. And this one becomes a tertiary carbocation, which we know is very stable. And so that's why you totally end up with that tertiary substituted benzene ring. Okay. All right, so again, it's just another limitation, something that can go wrong. If you're designing out this reaction sequence to get a specific product, these are potential pitfalls. Hydride shift or alkyl shift. Okay, well, the other way you can, or the other thing that you can add to the benzene ring is an acyl group, or it's called acylation. I'll bring, well, you've already got it in your handout there, but we'll explain what we mean by that with some structures on the slide here in just a second. But so the acylation reaction is a reaction of an aromatic ring with a carboxylic acid chloride in the presence of the same catalyst, aluminum chloride, resulting in an acyl group substitution. Okay, so what is an acyl group? Well, this is what we mean by an acyl group. So, this R, remember, that's an abbreviation. It could be lots of things. But this right here is what we mean by the acyl group. You got it always has the C double bond O. That's the bedrock. It's got to have that. And then the rest of it's just got to be some carbon containing thing. This could be a methyl, it could be an ethyl, it could be a tert-butyl, it could be something really large and hard to characterize. But an acyl group is that hydrocarbon or part with a carbonyl. We're going to connect that to a benzene ring. For example, a reaction. So let's say I have this acetyl chloride. So again, notice I've got the halogen, the chlorine is there, and so it's the same mechanism, which we'll get in the next slide. But we form the carbocation, and then the carbocation acts as an electrophile with the benzene, and it substitutes a hydrogen to produce, in this case, acetophenone. Okay, so once again, here is a more similar, just another description of the mechanism. It's very similar to the mechanism of the Friedel-Crafts alkylation. It is a Friedel-Crafts reaction, but it's called Friedel-Crafts acylation rather than Friedel-Crafts alkylation. And it does have the same limitations. So similar to mechanism to Friedel-Crafts alkylation, and also possesses the same limitations on the aromatic substrate. Okay, so as I said before, this is just a more detailed picture of what's going on with the mechanism. So because you've got this halogen here, It just behaves again as a nucleophile with the aluminum being like your Lewis acid. It attacks the Lewis acid. And so then the electrons from that bond go onto the chloride, and that gives you your AlCl4 minus, okay? And that leaves a positive charge on the carbon. But in this case, it has gained stability because of a resonance forms. It's got resonance, right? So that positive charge, if we move the electrons from the oxygen, the lone pair of electrons from the oxygen to make a triple bond between the carbon and the oxygen, then the positive charge moves over to the oxygen, right? So due to resonance, it's got some resonance stabilization. It's delocalized. That positive charge is delocalized. So that means it's more stable, right? And then it behaves as an electrophile. So that positive charge then gets attacked by the nucleophile. There's your nucleophile, just like before. And then the catalyst comes back and takes away the hydrogen as it gives up its electrons back to the ring to give the aromatic ring once again. And so you end up with the acyl substituted benzene ring. Okay, so finally, let's think about, again, we're going to reverse engineer this product here. So think about what compounds might be used in a Friedel-Crafts acylation to prepare this product right here, okay? Well, you know, we've been talking about just using benzene, so let's put that down as one reactant, right? Just a benzene ring. Okay. So that's kind of like this part. Okay. And so the question then becomes, well, what would I use to get the other part of the molecule, the other part of that product? So I'll draw, we got the carbon double bond oxygen, and then the connection to the phenyl. I'm just going to put pH for phenyl, if you don't mind. The benzene ring, right? Just that's the pH is just an abbreviation for that benzene ring. And so what have we been talking about? Well, we've got to have a halogen in there somewhere. So let's just do that. Let's put a chlorine on there. Okay. So now remember what happens is there's a hydrogen right here. So that hydrogen and that chlorine are going to form this HCl. And in the meantime, I'm going to form that connection between that carbon and the carbonyl and that position in the benzene ring. So it's a substitution. I substitute out that hydrogen for this acyl group. And that's what gives you the product. All right, so once again, just to make it look prettier, I think I've got it. Yeah, there we go.